do that. And so the cycle now is you use case-based reasoning to drive the avatar, you get some feedback from the environment or from the user, do this trace analysis, look at a library of past traces, calculate differences, and then go in and automatically reauthor the behavior automatically, or suggest to the user when he next logs in what might be wrong and how the behavior might be fixed if you want the user to have the ultimate control. That's an application question. And the behaviors are then reinserted back to the case library in order to drive the avatar. So the vision here is to help a user create AIs by building these kind of self-adaptive tools, self-preparing tools, or self-debugging tools. Again, we have some good results now from the experiment showing that the system actually works quite well and helps people create, kind of achieve a better level, a higher level of creativity and expressivity with the same tools if you add this kind of AI feedback loop using Meta CBR. Third idea is behavior demonstration. So let's make it even easier. Okay, so we're all familiar with puppeteers. In the old days we had puppets, and we would have these marionettes that would try to act out your behavior because you were controlling them. Why don't we do the same thing for World of Warcraft or Second Life or whichever game you're trying to program? Let the user drive the avatar for a while, show us how the avatar should behave, and then you let go of the strings and the avatar keeps doing what it's just been learning from you that it should be doing. That's kind of the idea, let the system do the programming automatically. And so here again the CBR idea comes in. The system we built is called Darmok 2. People know what Darmok means, right? It's, if you've seen Star Trek, Next Generation, there's an episode called Darmok where Picard and the Enterprise goes off to another planet and meets a race of people that speaks entirely using case-based reasoning. It's one of my favorite case-based reasoning movies. And we had a lot of Trekkies in our group, so they called this Darmok after that episode. The other one, by the way, is Groundhog Day. People haven't seen that. It's not a great case-based reasoning movie. So it's a game-playing system, but the CBR part is domain independent. So if you want to try this in other domains, you can. We released it publicly on SourceForge. You can go download it. It's open source. You can add to it if you like. So this is kind of how it works at a high level. We have a user here who's going to play the game. The user's gameplay is treated as a demonstration for a learner that will learn cases. We don't know from a couple of experiences of watching you play a game what the general strategy is. What we do have is an example, or a couple of examples of playing the game. That's exactly what CBR is well suited to do, right? Which is take examples and then try to tweak them for the future situation. So we're going to use that to build up a case base and then use a planner to go in and modify these at runtime. The cases are represented as using Petri nets, or in particular hierarchical Petri nets. Why Petri nets? We found we needed inside these games a representation language suitable for representing that rich complexity I mentioned earlier. We have sequential actions, we have parallel actions, we have conditional and probabilistic outcomes. We may have loops, we may have sub-goals, we have multiple actions executing at the same time. So Petri nets is a very nice off-the-shelf formalism. There are lots of good tools out there that works and can represent the rich complexity of this domain. In the current version of Darmok, the planner can use arbitrary Petri nets. The learner, however, currently is somewhat limited. We're not learning loops. If you do the same thing again and again and again, it'll learn a sequence of similar actions rather than recognizing there's a loop. And I have a student working on that. And so other kinds of improvements right now. So this is what a case looks like. Over here is an episode. Remember now, this is not generalized. It still says would greater than 300. It's an example I've seen. It's not a general purpose algorithm for solving this problem. So in this particular example, you were gathering wood of a certain amount. This was the state of the world. There was a player with gold, etc. And the game was, this particular strategy was successful. And so the system has now got this Petri net that represents an action plan, if you will, of achieving this goal under this circumstance. So let me give you a little more detail on how this works. This is how the architecture looks like in a little more detail. Up on top is the planning system. So there's the case. There's a real-time adversarial planner, because again you're playing against an enemy. So you have to be adapted Minimax and built a real-time Minimax system which can adapt these plans on the fly. If you have a simulator available, you do in some games, you don't in some, then you can actually use a simulator to help determine the value of different types of actions. You execute the plan in the game state, and then by watching your actions as well as the opponent actions, you get demonstrations that can then be fed into learning. So this is how the learning works. The input again is a demonstration trace and an ontology or a representation of the world state, the game state of the world. And we're going to produce these plans or cases. The demonstrations are basically game logs. It's a series of inputs at certain timestamps. So at timestamp number 5, in a particular game state, a player built a farm at a particular location. We're going to stick those into what we call a goal matrix. So these are all those game states and actions again that we just saw. Across the top, we've listed all of the goals and sub-goals of the game. We know this from the rules of the game. So G1 might be win wargets or win game. G2 might be build a defense. G3 might be find the enemy, attack a tower, etc. So very general kind of goal states. One of the problems we are working on right now is how we might identify sub-goals automatically. If you see a certain kind of goal game state being achieved multiple times by multiple people, you might hypothesize that's a good state to try to achieve, even if it's not in your goal vocabulary to begin with. So for this algorithm, we're assuming that the goals are given. And so the first step now is to extract linear plans. In this example, in order to achieve goal 1, win the game, if you perform action A1 all the way to A11, you're going to win the game. Now it's not guaranteed, but this is a case. It's an example of where this happened. So that is a plan you can extract. So there's A1 through A11. We extract the plan. We then look at the preconditions of these states. Remember, we don't have postconditions, but we do have preconditions. So we notice that, for example, the preconditions for games for number 6, building barracks, got achieved after 1, 3, and 4 got done. After we have to harvest enough resources, train up a peasant, etc. And then the trigger conditions for 6 are done. So we can take this linear plan and turn it into a sequential plan like that. We do the same thing now for all of the other goals. So this is goal 2, but maybe it got achieved after game stage 6. And so we build up the same kind of hierarchy. And then we notice that there's a subpart of the red box here, G1, that helped you achieve G2, the black box. And so we can take G1 now and take this whole big net that we had and replace that and say, well, what we need to do to get G1 is we need to do G2 and then do 8, 9, 10, and 11. And so by doing this, we've got this kind of hierarchical Petri net that we're starting to extract. So each of these now turns into a Petri net. So this is G2 again, a G2 followed by 8, 9, 10, 11, which is a goal of achieving G1. In this case, it was true. And if we do this repeatedly, we get things like this that I showed you earlier. We then stick them all into a case library. So from a number of demonstrations, we get these little snippet and episode pairs that become the case library. Now to play the game, we extract the most similar cases that we know of and try to replay them or adapt them. So for example, in this old example I had where we're going to harvest gold, train a peasant, train a knight, and attack a tower, remember I said we're going to defer the decision of how we attack a tower. Suppose it's time now to do so. We look in our case library to see, is there a game state that is there a case that we know of in a similar game state with a similar goal of attacking a tower using a knight? And we'll find one or more of these, we'll evaluate the similarity of these, find the most similar one, and then try that action. It may succeed, it may fail, but that's, given the knowledge we have, the best we can do. So the way we do this is we've tried a number of different approaches. This is a very good area for more research. I won't go back now, but How you actually now use these cases to do planning. This is an approach which was very reactive, where we take these different cases, figure out the recommendations they make, and use this almost like a reinforcement learning function approximator to try to approximate the action to be performed in the next step. This was a more kind of a hierarchical HTN planning type approach, where we take pieces of these old cases and try to compose them into a hierarchical plan. And this is the most recent version, which is this real-time minimax planner, where we take at the state we're in, take the different actions being suggested, and either assess their outcome, or if we have a simulator, try to simulate that at least a couple of levels deep. You can't go very far because these state spaces are huge. So there's a lot of research to be done here. These are three of the approaches we've tried for how we do this kind of on-the-fly real-time planning with partial information. We tested this in 3 different domains. We have more results now with additional domains, but these are the ones that we had published last year. And we picked these games for a reason. We picked these games because they're all very different types of games. On the left is S2, which is our own clone of Warcraft. It has the same game mechanics as Warcraft, but with simplified graphics. And the important factors in this game are the terrain, the resource planning, resource management, etc. Timing when you build things. In the middle here is a sort of classic tower defense game. And this is a game where you have to go set out troops. These green troops are coming in to attack the enemy tower. And so this is a lot of it is spatial formation, different strategic elements to the game. Battle City is kind of your classic, fast-paced. We're going to send tanks down these walls and shoot people as we see them. Much more of a reactive game, more determined. This game here, for example, is not very reactive. Things don't happen quite so fast as in a game like Pac-Man. We got some pretty interesting results. So the way you read this is, over here is how many different demonstrations you gave it. So we had people play the game, the test game either once, twice, thrice, up to 10 different times. So imagine you're trying to teach this game, you're trying to teach an AI how to play the game. So you say, okay, I'm going to show you. I'll go play the game 3 times. You learned my strategy, and now I've got an AI that can play like me. So this is where you'll be on 3 times. This is how often the AI you build wins against the built-in AI for these games. And so you notice that even with one demonstration, and remember, one demonstration is not one case. It's a whole trace over 4 or 5 minutes of playing, which breaks up into many cases. We're getting pretty good win rates with some of these games. And over time, we are increasing slightly, except for towers. I'll tell you in a second why. Battle City is the worst. This is this kind of fast-paced, reflexive game. There's very little strategy in that game. And so this concept of extracting goals and sub-plans, there's really not that much goal-based behavior to extract. Towers is very strategic. S2 is kind of in the middle and gets better over time. We're getting to almost about 80%, which is about the level of a human player. And these AIs are being created by non-AI people. We just got people who, undergraduates to come play the game, but they're not PhDs in AI building code for us. So that's pretty interesting. This was an interesting result. Towers actually, even with one example, does really well, and it actually drops slightly. It turns out that in towers, there's kind of there are different strategies for playing it, but if you're playing consistently, one game pretty much gives away your strategy. And if you play it many times, what we think is happening is the system is getting lots of similar cases and getting confused about the best ones to retrieve. So what this tells us is we need a better way to develop retrieval metrics or similarity metrics to find the right cases to use in different situations. So we've tried to put all of this together into an experience for average people. I'm a very big believer in taking research out of the lab. There's a nice blog by Ed Chi over at Xerox PARC, or now just called PARC, on living lab research. And the concept is that you can buy pizza for 20 undergraduates and bring them into your lab and do a research study with them, but that tells you nothing about how these systems behave out in the real world with real people.